So I'm going to test for convergence and divergence of the following series. Our goal is to use comparison test. In the method of comparison test, we usually start by a known series. For series, summation an, summation bn. If an is less than equals to bn, and if the larger series is convergent, you can conclude that the smaller series is convergent as well. So for this series, I'm going to break down the general term into smaller pieces. Let us begin. We're going to do a little bit of algebra and the properties of ln. Recall that from algebra, x can be written as e to power ln of x. ln and e, they are inverse of each other. They get canceled out. So wherever you see x, you can write it as e to power ln of x. We're going to use this property to rewrite. We are going to use this property to rewrite ln of n to power ln of n. So e to power ln of n to power ln of n ln of n to power ln of n is basically writing this as e to power ln of n raised to power ln of n. Now take a look what's happening here. This can be written as you have the same exponent. This is another algebra property. Recall that. If you have something like a raised to power n to power m, you can switch this around. It is a to power m to power n. This guy is your n, and this guy is the second power, the second exponent. So you can switch these around. So you can write this as e to power ln of n raised to power ln of n. Very good. Now get rid of e and ln. This guy is equal to n raised to power ln of n. So why it is helpful here? What's the reason? Note that the limit of ln of n as n goes to infinity goes to infinity. It's a large number. So we can conclude that ln of n is more than 2. Well, okay. Since ln of 2 is more than 2, it means that n raised to power ln of n must be more than n to power 2. What's the meaning of that? It means that if I flip this, you get 1 divided by n to power ln of n less than 1 divided by n squared. So what we showed so far, we showed that ln of n to power ln of n can be written as n to power ln of n. And also showed that that 1 divided by, let me just take this one and copy it here. Now we can apply comparison test. The series, the larger series here is the series of 1 divided by n squared, which is always convergent. Is a p series, p is equal to 2 more than 1, so this guy is convergent. What's the meaning of that? It means that the smaller series must be convergent as well. So the summation of 1 divided by n to power ln of n must be convergent as well. But remember that these two series are the same, since the summation of 1 divided by ln of n to power ln of n is the same as the summation of 1 divided by n to power ln of n. So our series is convergent as well. Let's recap what we did. Here we have the summation of 1 divided by ln of n to power ln of n. We're using the property of e and ln. Since e and ln, they get canceled out, you can write x as e to power ln of x. So basically, whatever we have, e to power ln of n to power n, which is basically written as e to power ln of n because of the property of the multiplication of powers. You can switch these two powers, basically. You have the same base, which is e. You get e to power ln of n raised to power ln of n. But e and ln, they get canceled out, so you're left with n to power something. That's why we are using the comparison test, because I have n raised to some exponents. But at the same time, since n goes to infinity, ln of n goes to infinity. So indeed, it's a number that is larger than 2. Why it is important? Because n to power ln of n must be more than n to power 2. Or if you flip these two, you get 1 divided by n to power ln of n less than 1 over n squared. But the series on the right-hand side is a p series, and p is 2, which is more than 1, so you end up with a convergent series. So the series on the left-hand side must be convergent. But the series on the left-hand side is nothing but 1 divided by ln of n to power ln of n, which it means that the series must be convergent as well.